and continuity or discontinuities notes. Continuity, okay, just means the graph of a continuous function will have no breaks, holes, or gaps. Okay, so we know a graph is continuous. Like an informal definition you probably have talked about in algebra and algebra 2 is if you can draw the graph without ever picking up your pencil, okay, that's going to be a continuous graph. Okay, if you have to pick up your pencil for whatever reason, there's a discontinuity somewhere on the graph. Okay, so here it asks us to draw an example of a continuous function. Okay, so you could draw anything you want. I'm just going to draw something with some changes, and we're going to do this. Okay, so I was able to sketch that curve without ever picking up my pencil. So that is a continuous function. Now, I'm going to pick another color. You can do it just in a darker or a lighter line, however you want to do it. I'm going to draw something that is not continuous, a function that is not continuous. Okay, so there are different types of discontinuities, different reasons you may have to pick up your pencil. Okay, so I'm going to draw a few different ones. I'm going to try and kind of mimic this shape so you can see. So I could have this, and then all of a sudden I get here, and there's a hole. Okay, so I had to pick up my pencil for that. Or I could come here, and there's an asymptote. Or maybe my graph stops there and then picks up here to continue, something like that. But this is definitely not continuous. I would have to pick up my pencil here to draw this hole. What's happening here? What does it look like? A vertical asymptote. So I would have to pick up my pencil because this is a separate piece of the graph. Okay, and then here, there's just like this big gap, a break in the graph, and then it continues. Okay, so there are several different ways or types that your graph could be discontinuous. Okay, but we need to make sure we understand the difference in continuous and discontinuous, and then we're going to talk about the different types of discontinuity. Okay, now limits, okay, in order for a function to be continuous, okay, at a given point, x equals c, the function must approach a unique function value as x values approach c, okay, and it has to do this from the left and right sides. Okay, so limits are a way for us that helps us define the continuity of our graph is checking the limits. Okay, so what a limit is it's a concept of approaching a value without ever necessarily reaching it. So this graphic here, whenever you see this key concept, that is like directly from our textbook. So you can see in this graphic, okay, it says in words, and sometimes the words are confusing. So we'll look at the symbols and the graphic. But it says that if the value of f of x, okay, so that's y, right? F of x is y. So if the value of f of x approaches a unique value L as x approaches c from each side, then the limit of f of x as x approaches c is L. Okay, so in that exploration that you did on Thursday in the quick notes box, we had written out the notation, but here it is again. So the notation is LIM, that's the abbreviation for limit, okay, as x approaches c, f of x is L. So this means the limit of f of x as x approaches c is L. So they're saying as we get closer and closer to c along the x-axis, our y value is approaching L. So you can see that on this graph Okay, the black dashed line, there's L, and here's C. So as we move along from the left toward this point where X is C, or from the right as we move along to that point where X is C. From the left and from the right, our Y value that we're approaching is L. So the Y values are both approaching L from the left and from the right. Does that kind of make sense? I think once we do some examples, it'll make a little more sense, but we're looking at what is our graph approaching? Like if I was tracing the graph from the left side, getting closer and closer to that X value, or from the right side, getting closer and closer to that X value, what is my Y value moving toward or approaching? Okay, so in this particular case, they're both approaching the same value, L. Okay, so you can only have this limit, okay, like this, when from the left and from the right, your function's approaching the same value. Okay, I'm going to zoom out a little now. So in this example, we want to make sure we understand the correct notation of limits. So it says we're going to use this graph. Which of the following is the correct limit notation for the graph of y equals f of x below? Okay, so they're all focusing in on this point here. Okay, where x is what? 3. Okay, what's y? Now, it's not actually equal to -6 because it's an open circle, right? But that's the place where the open circle is at -6. So what they're asking when we talk about limit, we're saying from the left side, as I get closer and closer and closer, as my x value approaches 3, what is my y value approaching? And it's approaching -6. From the right side, is if I come this way, the other direction, as I get closer and closer to 3 on the x-axis, what is my y approaching? Also -6. So that this means that the limit as x approaches 3 of f of x is -6. So how would that be written? Which one do you think? The one right in the middle? So the limit of f of x as x approaches 3 is -6. That's correct. Okay, so what's wrong with the other options? Right? These top two don't even tell us that we're finding the limit of f of x. They don't have what we're finding the limit of. And the first one doesn't even have what x is supposed to be approaching. Where on the graph are we supposed to be looking? So that's missing a couple of things. This one's got that x is approaching 3, but it doesn't have the f of x. Okay, here we've got the limit as x approaches 3. There's not supposed to be two equal signs here. That's excessive. And then here we're missing again, what is x approaching? Okay, so they all were either missing something or that one had an extra equal sign. This is the correct notation. Limit notation. Everybody okay with that? All right, in this example, they want us to write the limit notation. We have our function g of x equals x cubed. The limit as x approaches 2 of g of x equals 8. So how could I write that in limit notation? What would I put? Say it again. I didn't hear the beginning. Okay, so that's the abbreviation is just LIM. I don't have to write the whole word. Of g of x. So under limit, this is where you put what x is approaching. Okay, and then it equals 8. Does anybody agree or disagree? Get some yays or nays here? What do y'all think? Yeah, that looks good. That's correct. Okay. So the limit as x approach of g of x as x approaches 2 is 8 or equals 8. Very good. And that's true, right? If we think about it, if we think about a cubic function, the cubic function looks like this. It comes through the origin with its point of inflection there. What this is stating is that as we approach 2, which let's say 2 is here, okay, our y value is approaching 8. Is there a point at 2, 8 on the cubic function? Yeah, because from the left, as we get closer to 2, we're approaching 8. And from the right, okay, as it gets closer to 2, we're approaching 8. So that is indeed the limit. Does that make sense to everybody? Okay. Now, discontinuities. Okay, I drew up here in the pink a graph with 3 different types of discontinuities. Okay, so this graphic distinguishes between those 3 types, and you need to be able to distinguish between them when you have a graph. Okay, the first type is called an infinite discontinuity, and this happens for at a given point, x equals c, or at a given x value, I should say, not a point. Okay, the function value increases or decreases indefinitely. So it's going up or down to positive or negative infinity. So in this graphic here, this is a rational function. What is happening there? What's in the rational function here? This is an asymptote, okay? So when you have an asymptote and your function is approaching it, so it's not approaching some specific y value, right? It's approaching infinity. It's not approaching some specific y value from the left either. It's approaching negative infinity. Okay, so when this happens, this is a discontinuity, okay? And it's indefinite because it keeps going forever. So this is called an infinite discontinuity. Okay, and I'm just going to write the names bigger beneath each image. So an infinite discontinuity is when you have an asymptote like this. Okay, the next kind is called a jump discontinuity. When you have a gap in your graph like this, a break in your graph, okay, where they are not approaching the same, the limit is not the same from the left and the right. Okay, so what it says in words here is that the limit of the function as x approaches c from the left and the right exist, but have 2 distinct values. So from the left here, as we come on the left side of the graph toward x is c, we're approaching this y value down here, aren't we? Whatever this is. Okay, but as we approach x equals c from the right, we're approaching this y value here. Those are 2 different y values. So the limit from the left exists, the limit from the right exists, but they are not equal. That is a jump discontinuity. And then last but not least is called a removable discontinuity. Okay, this happens when your function is continuous everywhere except for a hole. So when you have a hole in your graph, that is called a removable discontinuity. Now, sometimes you'll see it written or drawn on some graphs where there will be a hole and then there will be a point somewhere else, like that. It's like that value was just moved down here to this y value instead of being up here for some reason. Okay, that's still removable, even though the point is showing elsewhere. Okay, there's still a hole in the curve or the line up here. Does that make sense? So infinite, jump, and removable. So you'll have to be able to distinguish what types of discontinuities you're looking at in your graphs. And when we get to, we're going to look at that check for understanding later. We're also going to have to be able to identify the type of discontinuity from a table. So if you have a table of values, okay, interpreting what the values are, how they're changing, what type of discontinuity is being shown in the table. And there's one on the check for understanding that we'll see in a minute. All right. So here's a fun graph. Lots of different pieces in this piecewise. We want to list where are the infinite discontinuities, where are the jump, and where are the removable. Okay, so guess let's start with infinite. Okay, so at what x values do you see infinite discontinuities? So what are you looking for infinite? Looking for where there might be an asymptote. Do you see any? I would say here, right? Looks like there's a vertical asymptote at x equals -3. Does it look like there's any other asymptotes on that graph? I don't see any. All right. So next up then, let's look at jump discontinuities. Do you see any places where this graph jumps? That means the limit from the left and the right are different. Okay, at what x values? Where do you see that? At 4? Well, no, at 4, this is just the graph. This is almost continuous. There's just this one little hole. What's that called? That one's called removable. Okay, so I'm going to go ahead and mark that. When you have that, that is removable. So when it's just a hole in the graph, that's removable. So that's x equals 4. There's a removable. Okay, so where do you see a jump? Like the graph jumps to a completely different place. Okay, so here and here. So I heard -6 and 6. What else? At 0. So there are 3 jump discontinuities in this one. So there are a total of 5 discontinuities in this piecewise. Feel okay about that? All right. So the last thing on here that I want to make sure that we have down is the conditions of continuity. Okay, so what has to be true for a function to be continuous at a specific point, x equals c. Okay, so the first thing that has to be true is that the function has to be defined at that point, meaning c has to be in the domain of the function. The function has to exist there, right? Okay, so, I mean, you can do this in your own words, however you want to say it. I'll say the function, and I abbreviate function FCN a lot. When you see that, that's function. So the function is defined at x equals c. And if you want to put in parentheses what I said, that means that c is in the domain of the function. Okay, so that's the first thing. The graph has to exist at that point to be continuous there. Okay, but that's not the only thing. The next thing that has to be true is that the limit must exist. Okay, so mathematically what that looks like, what the notation is that limit of f of x as x approaches c from the left. Okay, remember from the left is that little minus sign that was in the exploration from last week, has to be equal to the limit of f of x as x approaches c from the right. So the left limit, the left-sided limit and the right-sided limit have to be equal to each other for the limit to exist. Does that make sense? Okay. Now that those first two could be true and the graph still be discontinuous. Okay, so there's a third condition that has to be met, and it's that the limit that we just determined does exist is equal to or is the same as the function value at that point. Okay, and again, mathematically speaking, okay, what that means is that the limit of f of x as x approaches c must be equal to f of c. So if we actually evaluate the function at c, that answer that we get has to be the same as the limit was from the left and the right. So all three of those pieces have to be equal to each other for it to be a continuous function at that point. Okay, so looking here at this graph, like this point that's highlighted in blue, okay, at x equals 4, does the function exist? Is 4 in the domain? It is, because there's a point up here, right, where x is 4. So that's in the domain. So that meets the first condition. Is the limit from the left and from the right the same? Yeah, it is, because from the left, it's at the limit would be -2, and from the right, it would be -2. So it meets the second condition. But this one fails the third condition because that limit is -2. But if we evaluate f of 4, we get 4. So those are not equal, which means it's not continuous. Okay, because there's a hole there. Does that make sense? So that's what I mean when I say it has to meet these three conditions to be continuous. Okay, so let's look at the exploration page that you got last Thursday, that was. I believe most of you were confident and fine with the front, with the one that says, what's the price of gas? Did y'all feel okay with the front side of that? Okay. So down here at the bottom, that quick notes, this is what I was referring to, making sure you understand the notation. Okay, the little minus means from the left, that little plus means from the right. Those have to be equal to each other for the limit to exist here overall. Okay, so on the back was this scenario about getting hitched and meeting at Olive Garden. The bride and groom are trying to meet. Okay, so the scenario doesn't really matter, but let's just look through these and make sure that you answered these correctly. You can change things if you need to, or add if you left it blank. Okay, so we've got 1 is the x value we're trying to approach. Okay, so we can see here, there is a discontinuity, right? So as I approach from the left, okay, so that's the groom, it looks like. So as we're approaching from the left, what is the y value we're approaching? As we're getting close, as x is getting closer and closer and closer to 1, from the left side, what's the y value going toward? I'd say about 0.5, yeah. If you were around there, that's okay. You didn't have to be exact. Okay. And then I think this one is the bride. Okay, so from the right side, as she's getting closer and closer and closer to x is 1, what y value is she approaching? Did a lot of y'all put 2? Yeah, it looks like it's right below 2, but that's okay. We're just estimating. It's not going to hurt anything for us to be off a little on this one. Okay, so she's approaching, the y value's approaching 2. Now, are those the same? So can we have the limit as x approaches 1? No, because from the left and the right, we're approaching 2 different numbers. So this is a scenario where we would say does not exist. That abbreviation DNE. The limit does not exist. The limit does not exist. Y'all Mean Girls fans?
No, yeah.
Okay. Okay, so the limit does not exist here as x approaches 1. All right, now evaluate f of 1. Okay, so is 1 in the domain? Yes, it is. So we can get an answer here. Even though the limit doesn't exist, we can evaluate. If I go to 1, what is the y value there? That's the 2. That's the evaluation piece. Okay, so my limit was not equal to the function value. So this is not continuous. It doesn't meet those 3 conditions, does it? Okay, so that means there's a discontinuity. Can you tell me what type of discontinuity this was? That was a jump. I'm going to go ahead and just label these as we go, what type of discontinuity they are. All right, so in scenario 2, as the groom approached from the left, we're going toward -1 here. What y value is he approaching? 1. Okay, and the bride is coming from the right. What y value is she approaching? Also 1. Hey, so those are equal. Does that mean now I can have the limit as x approaches -1? Yes, and it's 1. Okay, so the limit from the left and the right are equal. That's good. So the limit exists. Okay, now I need to evaluate there at that point. Is that in the domain? -1? No, and it's not elsewhere either. It's not in the domain at all. So this is an undefined value. So the limit does not equal the function value. And this actually failed the first condition. The value -1's not in the domain. So we knew this was not going to be continuous at this point. What type of discontinuity is it? This one's called removable. When you have just the whole, that's a removable discontinuity. All right, so the groom was approaching 1 from the left. What y value is he going toward? As he gets closer and closer and closer to 1, what y value is he getting closer and closer and closer to? -infinity. So he's going to -infinity. Okay, what about the bride as she comes from the right side? What's she going toward? +infinity. Are those the same? No. So the limit does not exist. Okay, now is 1 in the domain? Can I evaluate f of 1? No, there's an asymptote there. That is another undefined value. Doesn't matter if it's a whole or an asymptote. Like the last one was a whole, this one was an asymptote, still undefined there. So what type of discontinuity was this? This one is an infinite discontinuity. So we had 1 of each type of discontinuity. And then scenario 4, it says the plan actually goes off without a hitch. We are approaching, what is it, 5. Okay, so I'm gonna put a point there at 5. Okay, so as the groom approaches from the left, what y value is he approaching? 0. And the bride is approaching from the right. What y value is she approaching? 0. So they are equal. So that means the limit does exist. So far, so good. Now, what about when we evaluate that? What is the value of the function when x is 5? Also 0. So the limit exists and it's equal to the function value there. So this one is a continuous function. There's no discontinuity. This one is continuous. So that answers that last question, which says which of the four functions is continuous. It was number 4. You can put in your own words why or explain that, but it meets those conditions, right? There's no hole, there's no asymptote, there's no jump. Okay, the limit exists, the value is in the domain, and the function value and the limit are equal to each other at that point. From Thursday, they should be in the Thursday folder. The folder's hanging on the left. Look in the Thursday one. There's 2 papers. Yes. All right, so now let's look at that check for understanding. You are not. You keep that page, that exploration page, keep that as part of your notes. You do not, yeah, you're going to end up keeping all of this as part of your notes. All right, so the check for understanding, the first one is similar to what we were doing on the notes page and there on the with the bride and groom. We're saying approach from the left, approach from the right. So what's the overall limit? And then evaluate. Okay, so you were doing that at -1 and at 3. Okay, so what you if you were able to do this on Thursday, great. If not, I think you should be able to answer those now, right? Does anybody still need me to go over this type of problem? It's like what we were just doing with the bride and the groom. We approached the number from the left, we approached the number from the right. So if they're the same, that's the limit. If they're not, it does not exist. We good with number 1? Does number 1 make sense to everybody? Okay, so you can fill that in. It's just some practice for you. Now, number 2, I do want to go over with you because there was not one anywhere else in the notes with a table. So let's think about this. Okay, we are trying to approach where x is 5. So this is the value we're looking at right there. Okay, so it says, what is the limit of g of x as x approaches 5 from the left? So we can see as our x values are getting closer and closer and closer to 5 from the left side, what is happening to these y values? They're getting closer and closer to what? No. Look at the, it's -7.88, -7.9, -7.99. They're getting closer and closer to -8. Okay, so looking at those x values as they approach 5, looking at the y values, they are approaching -8. Do y'all agree with that? Okay, then from the right, as the x values approach 5, look at what's happening to the y values going this direction. Okay, so it's -7.6, -7.8, -7.9, -7.99. So what are those also approaching? -8. So from the left and from the right, our limit is -8. So that means our limit exists, right? Yeah, that means yes, when those two things are equal, the limit from the left and the limit from the right, the limit does exist, and it's that value, -8. So the limit is negative as x approaches 5 is -8. However, that's not equal to the function value, is it? The function value is -14. So I'm just going to write this to the side. I'm going to say if I actually evaluate f of 5, I get -14, and that is not equal to -8. So what does that mean? What does that tell me about this function? Yeah, that 1 point is a lot lower. So what type of discontinuity would this be? This, I hear several different answers. So let's try and picture this. Okay, so from the left and from the right, I don't know where we are on the axis, but so let's say this is the y. Okay, so this is -8 and this is -14. So as my graph approaches this number from the left, And this, I can tell you exactly where this is, where X value is at 5. Okay. As we approach from the left, the numbers are coming down, or excuse me, they're going from negative, yeah, they're coming down to about -8 here. Okay. And same thing from the right. It looks like they are coming down to be more negative to -8. Do y'all agree? Okay. But then it doesn't exist there where you would think that they are going to meet at -8. They don't. It's way down here. So what happens here is there is a hole. So what type of discontinuity is that? So this is a removable discontinuity. So you need to be able to read this table and see, okay, from the left and from the right are equal, but it's not equal to the evaluation. That is a removable discontinuity, okay? You should be able to picture that without having, I mean, if you need to sketch it, I mean, no harm, no foul, but ideally you would be able to see that just by looking at the tables and the values in the table. Yes, so there you will have to be able to recognize from a table, okay? So if this, so write a sentence explaining your answer in part C means. So this means that the limit exists. So the limit as X approaches 5 exists, okay? But I'm going to add what we just talked about, okay? So the limit exists, but it's not equal to f of 5. So there is a removable discontinuity. Because remember, in the notes, when we were looking at the definition of the different types of discontinuities, we said if the limit from the left and the right are the same, but it's not equal to the value, that's a removable. In this table, what would the values have to look like if it was a jump discontinuity? Wouldn't the left and right side be approaching completely different numbers? Okay, so if your left and right are approaching distinct numbers, different numbers, you'll know that it's a jump discontinuity. Okay, if the values are approaching infinity or negative infinity, that would mean you're approaching an asymptote, right? It's going down forever or up forever along an asymptote. So that is how you would know that it is a infinite discontinuity. All right. And there is a practice in the Delta math with making a table. So you'll get a little bit of practice with that. Okay, on 3, you were sketching. There's tons of possible answers here. If the limit as we approach 3 exists, that means we can just have a point at X equals 3, right? Or I'm sorry, it says it does not exist. Okay, so the limit does not exist. That means it can't be a point there and it can't be a hole there. It's got to be either an asymptote or a jump at 3. So I'll make mine some sort of jump, okay? And then I don't know what it does to the other side. That can vary. But for the limit as we approach 0 from the left, it has to be up at 2. So that means that we want to either have a hole at 2 or a point at 2. So I'm just going to put a point there. So this could be a graph that meets those requirements. There's a lot of possibilities there. But just know for the limit to not exist, you had to do either an asymptote or a jump here where X was 3. All right, and last but not least on 4, it's asking, it shows the graph from -5 to 12, determine all the different types of continuous, where it's not continuous and classify. So I'm recording right now, so I'm going to go ahead and finish this. If you want to go back and look at it later, you can. You're not turning any of those papers in. You are just doing the Delta math practice. Okay, so let me finish this recording real fast. Okay, so this one is a whole, and this one is a whole. So both of those are removable. Okay, this right here is a jump, and this is a jump. Okay, and then here in the middle, we're approaching negative infinity and positive infinity like that. There's an asymptote, so that is an infinite discontinuity. Okay, so I'm gonna stop the recording.